Assalamualaikum. Today we're gonna learn about forward converter, which also known as isolated buck converter. Previously, we have learned about flyback converter. So today we're gonna focus more on the forward converter. The difference between the flyback converter and forward converter, both is isolated, the same, but the difference is the isolation in forward require transformer and also inductor, and isolated forward require transformer and one inductor for each output, which we're gonna later see in the examples. And normally forward converter are used at higher power compared to the flyback converter. Okay, so here is the example of the schematic of the forward converter. Okay, so if you can see here, we use a transformer in the forward converter, and of course we have the primary side and also the secondary side. So this is the basic schematic of the isolated forward converter. Okay, to add the transformer for isolation. Okay, the reason for isolation is because at high power, so at high power, we want to isolate the primary and secondary. Why do we isolate primary and secondary? Can you imagine the incoming voltage source, will be about 100 megawatt or 140 voltage, or maybe 5,000-6,000 volt. So what will happen if something happen at the primary side, if we have discrepancy in the voltage source, or we have some disruption at the voltage source, what will happen without the isolation, without the transformer? It will definitely damage our load. Our load is normally the components that we use, can be our appliance, can be the fridge, can be the TV. So you don't want that, for example, to happen. So to be safe at a high voltage such as 200, 400 volt, we have an isolation. So this isolation important because we can save our load. If something bad happen at the input, some fault happen at the primary side, it will not damage the secondary component. All right. But however, this basic idea of the forward converter has a problem. The first problem, the transformer will not pass the DC component. We're going to have a look. So for example, so we have a switch S. This is a switch. So this is what we mean by when the switch is on. So when the switch is on, so it will get connected. So what will happen? Of course, we have a voltage source. Of course, we will have a IS flowing, right? So IS will flow when the switch is on, through the N1 winding. Right. So this IS now, you know that with the formula of the transformer, IS is related to the secondary. So the secondary we have ID2, all right. So we relate IS with ID2 using the transformer ratio, this one. But now, because we are using a transformer, we have an additional guy here. So this additional guy we call I magnetizing. So how do we get I magnetizing? So remember a transformer here, we have a winding. So this winding is made from the coil. So this coil, just remember do you remember your physics? So when you have coil, okay, you have a magnetic field. Okay, so when the currents pass through the coil, you will create a magnetic field. So this magnetic field will actually generate a I magnetizing. So that's why you have an additional here, I magnetizing. Okay, right. So let's continue. So now let's turn off this guy. Let's turn off the switch. Okay, so now when the switch is turned off, okay, means that ID2, okay, will flow, okay, based on the formula here we have here. ID2 will flow inside the secondary circuit. Good. Okay, but then what happened to IMAC? Okay, IMAC has nowhere to go. Okay, so this IMAC has nowhere to go. So what will happen? Okay, IMAC has nowhere to go. So it's in this loop. Alright. So this will end up blow up the whole circuit. Okay, so what happened? Bang. Okay, alright. So how are we going to solve the problem? Okay, here's the solutions. We're going to make path, okay, for the energy stored in the T, okay, alright, so that it can go back to the supply when the switch S is off. So how are we going to do that? So we're going to add another third winding, okay, inductor called N3. Okay, so let's have a look the schematic now. Okay, so this is the complete schematic of the isolated forward converter. Okay, so this is the schematic that you guys have to learn and know how to draw. Okay, unless it's provided in the final question, then you don't have to draw, otherwise you have to draw. Okay, so let's look in this schematic. What's new now? Okay, this guy are new. Okay, so these guy are called N3. Okay, the third inductor winding we just add here, and then we add an additional diode as well. Okay, right. So in this schematic, if you see here, okay, now, okay, when the switch is off, okay, when this guy is off, all right, so now the current can flow back and out. Okay, what current? The IMAC. That's good, isn't it? Okay, so this is very brief. So now, okay, in the next slide, I'm going to show you, okay, the details. Let's have a look when the switch is on and also when the switch is off. All right, the operation. Okay, something for you to note down. Okay, all right. You have to remember that this N1 and N2, okay, and also N3. Oh, sorry, N1 and N3 are wound closely together. Sorry, N1 and N2, of course, there's air gap. They cannot be close, okay? Right? But N3 and N1 are wound together. So means that they're bipolar, they're very closely coupled magnetic. Means that, okay, the air gap almost zero because they are very close together. Okay? Alright? So it's not like N1 and N2 where we have an air gap. Okay, when we have an air gap, it's not called bipolar. All right, okay, so because it's really close, okay, together, you can assume N3 equals to N1 and V3 equals to V1. Okay, all right, so next, let's have a look. Okay, so here's the isolated forward converter, and we're gonna try, okay, to see, okay, when the switch is on. Okay, all right. So what happened if the switch is on? So this guy is connected. Okay, so this is as on. Okay, right. Before we actually start, let's label each of the component. Okay, all right. So let's put the label. Let's say this one is plus minus V2. This is plus minus V1. This is plus minus V3. Sorry. Okay. All right. And then let's label this as D2. This is D1. This is L. Okay. All right. So let's label this guy as D3. Okay. So let's solve this problem. Okay. So when S is on, okay, two things will happen. Okay. One at the primary side. Okay. Let's put a cap. And this at secondary. Okay. When S is on, first thing, okay, let's use another different color. Okay, all right. So when S is on, what will happen here is the current, the IS, will flow right here. So this is IS, but the current cannot flow here. So of course the diode will be a reverse bias. Okay, so if the diode is reverse bias, definitely the D3 is off. Okay, so if D3 is off, what are you expecting? ID3 is 0. Very good. Okay, so now we have V1. Okay, so V1 potential is now equals to the V supply. Okay, and you know that V2 using the ratio of the transformer. Okay, you get this one. And then of course V3 is 0 because there's no current flowing in V3. Okay, so that is for primary side. Let's see the secondary side. Okay, so the current now, okay, flowing. So this current, okay, will flow, but then D1 will become reverse bias. Okay, so D1 is off, but D2 is on. Okay, so in here, your ID equals to, okay, you agree? Because now, this is your ID2. The one flowing here is your IL. Okay, because there's no disjunction, of course the ID2 will be equal to IL. Okay, for IS, remember the formula IS given previously? Okay, plus Imax because now the ID2, okay, because now the ID2 is equals to IL, you can rewrite IS as N2 N1 IL plus Imax. Okay, this formula is important. Okay, alright. Because later we're going to draw the waveform, so it's important to know the gradient. The gradient of IL. And you know the gradient of IL is from this point to this point. So we call it DIL over dt. Okay. So if we apply KVL, okay, if we apply KVL at the secondary, this is secondary side. Okay, we start from here. We see the negative first. Okay, oops. Okay, so negative Vs plus Vl plus V naught. Why plus? Because this is plus minus VL plus minus. And we see the plus sign first, so that's why it's plus. Okay, VL. Alright, then we shuffle the equation so that we get, sorry, not Vs, V2, yeah. Okay, V2, VL plus V naught. Okay, so if we replace V2, we get N2 by N1 Vs VL plus V naught. Okay, remember the formula DIL dt equals to VL. Okay, and we reshuffle everything. We will get, oh sorry, DIL over dt equals to okay, so this formula here is important, okay, when we draw the waveform later. Okay, it shows the gradient of the IL. Okay, so let's see when the S is off, what happened. Okay, okay, when the S is at the off state, okay, you will see something slightly different. Okay, now you see that D3 is on. Okay, this color is not really clear. Okay, so now you see that the color is, sorry, D3 is on. Okay, and V3 is also on. Okay, alright, so let's have a look at the schematic. Okay, again, let's label all the components. So now the S is off. So this is D3. Okay, this is V3. This is V2. Sorry, V1. V1. That is V2. Okay, this is D2. And this is D1. And this is L. Alright, okay, so what we're trying to solve in this slide is what will happen when the switch when the switch is off. Okay, all right. Normally, in other converter, you learn that, okay, all the converters, in the typical converters, okay, you only have two states, as on and as off. Typical. But in isolated forward converter, it's different because you have three states. One when the S is off, when the S is on and off, okay, that is two states. And you have another guy. Okay, this one is called S off, but after the call reset. Okay, so this is special, okay, just for isolated converter. So you have three states. Okay, so we have done so far, we have done, okay, S on, okay, and now we are doing the S off. Okay, so let's do S off first. Okay, so what will happen in the S off? Okay, there's no current flowing in this path, so means that the current now, okay, no current. Okay, so what will happen when the switch is off? Okay, the flux here, at the T, the transformer, okay, will try to decay, okay, and make the polarity of the V1 and V3 to reverse compared to the Vs. So now we have a reverse polarity of a V1 and V3. Okay, so now because we have a reverse polarity, so now the D3 are on and become a forward bias. Okay, and now because, okay, now we are decaying, so there's no supply, so now the ID2 is off. Okay, all right, so what will happen here at the secondary? Okay, now the D1 will be on and the IL flows through the diode D1. Okay, so let's have a look at the equations. Okay, so let's draw for primary, what happened in primary, and this is secondary. Okay, so in primary, because now our diode is turned on, so the ID, there's a presence of ID3. Okay, so here the V3 will become negative Vs and V1 will become negative Vs. Yeah. Okay, for secondary, the V2 still, but this time we have negative ratio, yeah, of Vs. And then of course IS should be here. Okay, S is 0, and then ID3 is now the Imax. Okay, so if I say if it's in the gradient, okay, so because we always want a gradient, so the gradient always in the form of a differentiation of the current over time, because it's the difference between two points, yeah, and then so that is negative Vs over L1. Okay, right. So now you see that, okay, this from this, okay, you can see now the flux are not trapped. Okay, so now we can pass the energy all back to the supply. So because thanks to this third winding, yeah. Okay, so now we have done this part. Okay, next we're gonna have a look. Okay, what happened during this time when the S is off after the core is reset. Okay, so in this part is still the switch is still off. Okay, but this is during or after the core is reset. Why is the core reset? Okay, the core is of course here, the transformers. Okay, all right. So now, okay, sorry. Okay, so now what happened is IMAC. Okay, remember the IMAC? IMAC will flow in D3, okay, and also N3, and return back to supply. Okay, so if you see here, now IMAC is also known as ID3. Okay, all right. So during the core reset, okay, the diode D3 is off. Oh, I cannot erase that diode to make it open, but okay. All right, but you see this now become open. Okay, so what's happening here is, okay, during the core reset, the IMAC, okay, will try to flow out, okay, to the supply. Okay, so the IMAC, all right, will try to flow out to the supply. Okay, all right, so this diode is still at open, okay, reverse bias, so we will cancel that diode. Okay, all right, okay, so this is still at off. Okay, all right, so IL still flowing from ID1 to the inductor and out to the output voltage. Okay, so this core reset will happen until all the magnetizing current is 0. Okay, so let's have a look. So IMAC, so the core reset will happen until all the IMAC reach 0. Okay, so when this happens, okay, D3 is off and IL continues to flow. Okay, to flow through D1. Okay, where is D1? Here is D1, so keep on flowing. Alright, so we can say that ID1 equals to IL. Okay, and of course ID2 is 0. Okay, and short form we can say the ideal T is over negative VR over L. Okay, this for the gradient of IL. Sorry, it's going to be negative. Okay, alright. Okay, so that is the operation of the isolated forward converter.